In this module, you will study about electric current, EMF and electric potential. Learning objectives. Understanding current is the rate of flow of charge and recall and use the equation I equals Q divided by T. Effects of current. Direct current and alternating current. Current in series and parallel circuits. Distinguish between the directional flow of electrons and conventional current. Measurement of current. Potential difference and EMF. Voltage in series and parallel circuits and measurement of voltage. Electric current. An electric current consists of moving electric charges. In a metal, each atom has one or more loosely held electrons that are free to move. When a cell is connected across the ends of such a conductor, the free electrons drift slowly along it in the direction from the negative to the positive terminal of a battery. There is then a current of negative charge. The electric conductor shown here is connected to a dry cell. The left side of the conductor is connected to negative terminal of a cell and the right side is connected to positive terminal of the cell. The electrons repel from the negatively charged terminal and attract towards the positive terminal. During its motion, electrons collide with the atoms. Electric charge and electric current. If we connect a metallic conductor to a dry cell, a large number of electrons flows from the negative terminal of the cell to the positive terminal of the cell. If n represents the number of electrons flowing from negative to positive terminal, then electric charge is given by Q equals n into E. Q is the charge, n is a number and E is the charge of one electron. Now, electric current is defined as the amount of charge flowing in unit time. So electric current I is equal to Q divided by T. That is, I is equal to NE divided by T. So we can say electric current is the rate of flow of charge. Also we can say electric current is the flow of electrons because charge means a group of electrons. If large number of electrons flowing through a conductor, the current in the circuit will be high. Effects of current. When electricity is allowed to pass through a conductor, electrical energy can be converted into heat energy, light energy, or it can make some magnetic effect. Sometimes we can convert electrical energy into chemical energy. In electric iron or electric heater, we can convert electrical energy into heat energy. In fluorescent lamp, electrical energy is converting into light energy. Now, if you keep a magnetic compass near a current carrying wire, we can see a deflection happening in the magnetic needle because electric current can interfere with the magnetic field. When we charge a battery, for example, if you charge our laptop or mobile phone, electrical energy is converting into chemical energy of the battery. Chemical reaction happening inside the cell gives a positive potential to one electrode and negative potential to another electrode. That is, there will be deficiency of electron in one electrode and excess electrons in another electrode. As a result, electrons move through the conductor and reach the other terminal. The battery provides electrical energy to the electrons. The electrons move through the LED bulb and electrical energy will convert into light energy. When electrons pass through the resistor, they collide with the atoms. This will increase the vibration of atoms and molecules in the resistor. As a result, heat energy will develop in the resistor. Electrical energy will convert into heat energy. Unit of electric charge and electric current. The unit of current is the ampere. Current is measured by an ammeter. The unit of charge is coulomb. An ammeter is connected in series with a circuit to measure the current. An ammeter is a very low resistance instrument. 1 coulomb is the charge passing any point in a circuit when a steady current of 1 ampere flows for 1 second. That is, 1 coulomb equals 1 ampere second. Direct and alternating current. In a direct current or DC, the electrons flow in one direction only. In an alternating current or AC, the direction of flow reverses regularly. An example for direct current is the current from a dry cell. You can see a steady AC. Time is plotted along x-axis and current is floating along the y-axis. And we can see the magnitude of current is always same, and electrons always flowing from the negative terminal of the dry cell to the positive terminal. Now you can see a varying DC. Here electrons always flowing from one terminal to another terminal, but the magnitude of current is varying. Now in the third diagram, you can see an alternating current. An alternating current produced from an AC dynamo. Here initially the current is 0 and the number of electrons flowing from one terminal, say terminal A to terminal B, is increasing. It reaches a maximum value, then reduces to 0. After that it will change the direction. So far electron was flowing from A to B, but now the electrons will start flowing from B to A. Again, the number of electrons flowing from B to A will increase to the maximum value, then coming back to 0. So the AC completed one cycle and the cycle will repeat. The number of complete alternations or cycles in 1 second is the frequency of alternating current. The unit of frequency is the hertz. Electric current in series circuit. In a series circuit, the different parts follow one after the other and there is just one path for the current to flow. The current is the same at all points in a series circuit. Here you can see a dry cell connected to 3 ammeters and 2 bulbs. If 100 electrons coming out from the negative terminal of the dry cell, it will pass through all that ammeters and bulb and reach the positive terminal of the dry cell. So the same number of electrons will pass through all the components and all ammeters will show the same reading. The current in this circuit is 2 ampere. Electric current in parallel circuit. You can see a dry cell and 3 lamps connected in parallel. A1 is an ammeter used to measure the total current in the circuit. A2, A3 and A4 connected with each bulb to measure the current flowing through the bulb. In a parallel circuit, the lamps are side by side and there are alternative paths for the current. The current splits. Some goes to the first lamp, some goes to the second lamp and the rest to the third lamp. The sum of the currents in the branches of a parallel circuit equals the current entering or leaving the parallel section. So here A1 is equal to A2 plus A3 plus A4. You can see the flow of current from positive terminal to negative terminal. The current splits while passing through the resistors and reach the other end. In series circuit, components are connected one after the other. There is only one path. So if one instrument damage, for example in this circuit, if one bulb damage, it will affect the flow of current in the entire circuit and there will be no glow for the remaining bulbs. In parallel circuit, current is splitting through the components. So even if there is damage for one component, it is not going to affect the other components. Here you can see 3 bulbs. If something happens for the middle bulb, this first and last bulb is not affected. This parallel connection is used in house wiring. There will be 2 terminals. One is called the live wire, another is called neutral wire. One wire from the bulb is connected to the neutral wire. Another wire from the bulb is connected to the live wire through switch. So because of this parallel connection, if something happens for the electric bulb, it is not going to affect the electric fan or any other electrical instrument. Direction of current and direction of flow of electrons. You are familiar with electrical circuit. So whenever you look at the diagram, you can see the direction of electricity is shown using arrow mark from positive terminal to negative terminal. But we already know that the flow of electricity is due to electrons. The flow of electrons is termed as electron current. Electrons flow from the negative terminal to the positive. Conventional current or simply current behaves as if positive charge carriers cause current flow. Conventional current flows from the positive terminal to the negative. Before the discovery of electrons, scientists believed that electric current consisted of moving positive charges. Although this belief was later proven wrong, the idea is still widely held. So whenever you draw electric diagrams, you have to show the direction of current from positive terminal to negative terminal. Ammeter. Ammeter is used to measure electric current. It is a low resistance instrument. There are 2 terminals on the ammeter. The negative terminal is often black and the positive terminal is often red. The negative or black terminal we have to connect to negative terminal of the cell, and the positive or the red terminal we have to connect to positive terminal of the source of current. Here you can see some readings of ammeter. So in the first picture, the least count is 0.1 ampere. Between 0 and 1, you can see 10 divisions. So the value of that 1 division, that's the distance between 2 adjacent lines, that is called the least count. Here it is 0.1 ampere. Now the current is 0.5 ampere. So in the second picture, you can see left down picture, least count is 0.05 ampere and the current is 1.15 ampere. That last one is used to measure very high current. Here the least count is 10 ampere and current is 170 ampere. Least count is the minimum value that we can measure with the help of that instrument. So far we studied about electric current. Now let us study about potential difference. A battery transforms chemical energy to electrical energy. Because of the chemical action going on inside it, it builds up a surplus of electrons at one of its terminals, the negative terminal, and creates a shortage at the other end, the positive terminal. It is then able to maintain a flow of electrons, that is, an electric current, in any circuit connected across its terminals for as long as the chemical action lasts. Now, let us try to understand what is electric potential. You can see a circuit here. If you imagine that the current in a circuit is formed by drops of electricity, each having a charge of 1 coulomb and carrying equal sized bundles of electrical energy. These bundles of electrical energy, we can call it as Mr. Coulomb. So Mr. Coulomb represents one such drop. As a drop moves around the circuit, it gives up all its energy, which is changed to other forms of energy. Note that electrical energy is used up in the circuit or in the resistance and not charge or current. As soon as a circuit is complete, energy is delivered from battery to electrons and then electrons to lamp or resistance. The model is helpful, but it is not an exact representation because energy is delivered at once to all the electrons in the connecting wire. So electrons carry that energy and come out from the battery. While passing through the resistor, the electrons losing its energy. It is converting to heat energy, light energy, or any other forms of energy. And the electrons coming to the battery, they possess less energy. Again, a chemical reaction happening inside the cell, and the cell will give energy to the electrons. Again, the energy is used up in the circuit or in the resistor, and this process continues. So, if the voltage or potential of the cell is very high, it can give more energy to the electrons. e.m.f, electromotive force. The potential difference at the terminals of a battery decreases slightly when current is drawn from it. This effect is due to the internal resistance of the battery, which transfers electrical energy to heat as current flows through it. The greater the current drawn, the larger the lost voltage. When no current is drawn from a battery, it is said to be an open circuit, and its terminal potential difference is a maximum. This maximum voltage is termed the electromotive force or e.m.f of the battery. The electromotive force E of the source is the energy supplied to the unit charge by the cell. Electromotive force e.m.f equals lost volts plus terminal potential difference. The e.m.f is defined as the number of joules of chemical energy transferred to electrical energy and heat when 1 coulomb of charge passes through the battery or cell. Or in another way, you can say, suppose we have a dry cell. Without connecting any other components, we can measure the maximum potential difference between the positive and negative terminal using a voltmeter. Then that voltage is called e.m.f of the cell. It is not a good practice to connect an ammeter or a voltmeter directly to the positive and negative terminal of the cell. Usually we connect voltmeter and ammeter in circuit, so there will be some resistance. Otherwise it may damage the voltmeter and ammeter. The volt. Potential difference is measured in volt, and the term voltage is sometimes used instead of potential difference. The potential difference between 2 points in a circuit is 1 volt if 1 joule of electrical energy is transferred to other forms of energy when 1 coulomb passes from one point to the other. In general, if E is the energy transferred or the work done, when charge Q passes between 2 points, the potential difference between the points is given by V equals E divided by Q, or E equals Q times V. If Q is in the form of a steady current I flowing for time t, then Q is equal to IT, or E is equal to I times T times V. That is, E is equal to VIT. Voltage in series circuit. Here you can see a cell connected to 3 lamps L1, L2 and L3. The voltage at the terminals of a battery equals the sum of the voltages across the devices in the external circuit from one battery terminal to the other. Here V1 represents the potential drop across the bulb L1, V2 the potential drop across L2, and V3 the potential drop across L3. So if we measure the potential difference between the point X and Y, that is between the two terminals of the cell, then V will be equal to V1 plus V2 plus V3. For example, if V1 is equal to 1.4 volt, V2 is equal to 1.5 volt and V3 1.6 volt, then V equal to 1.4 plus 1.5 plus 1.6 volt equal to 4.5 volt. Voltage in parallel circuit. Here you can see a cell connected to two lamps L1 and L2 in parallel. In parallel connection, the current will split between the bulbs. So more electrons will pass through low resistance instrument. So if there is an easy path, then more electrons will pass through it, and if there is a difficult path, then less number of electrons will pass through it. But if you measure the potential difference across this bulb, then it will be same. So here the voltage across the devices in parallel in a circuits are equal. Here V1 is equal to V2. Let us study some series and parallel circuit. Here you can see the terminals A and B. Between the terminals A and B, the two cells are connected. Each cell provides energy to the electrons present in the circuit. And the net voltage is 1.5 volt plus 1.5 volt equal to 3 volt. Now let us see the cells connected between the terminals X and Y. Here the cells are connected in opposite direction. So the first cell try to move the electrons from left to right. The second cell try to move the electrons from right to left, and as a result the net e.m.f, the net voltage in the circuit will be 0. So 1.5 plus minus of 1.5 equal to 0 volt. Now in the third circuit you can see the cells are connected in parallel. So the first cell give some energy to the electrons and it will move through the conductor. The second cell provide energy to another group of electrons that also will move through the conductor. But the voltage measured between the terminals will be 1.5 volt. Measurement of voltage. A voltmeter is an instrument for measuring voltage or potential difference. It looks like an ammeter but has a scale marked in volts. Whereas an ammeter is inserted in series in a circuit to measure the current, a voltmeter is connected across that part of the circuit where the voltage is required, that is in parallel. Here you can see an electric circuit. An ammeter is connected in series with the circuit and voltmeter is connected parallel to the resistor. Here you can see voltmeter reading. So in the first picture you can see between 0 to 1.5 there are 10 divisions. So the value of one division is 1.5 divided by 10 equal to 0.15 volt. So 0.15 volt is the least count, the distance between two adjacent lines. And the voltage shown here is 1.8 voltage. Now here in the last picture, the least count is 10 volt and the voltage shown here in the instrument is 390 volt. Thank you. If you like this video, you can subscribe and share. If you have any suggestion or some questions, you can type in the comment.